Hello and welcome back once again. So, right now we are talking about the fracture behavior of discontinuously reinforced aluminum based MMCs, and with regard to that we discussed about the fracture behavior of the metallic matrix in the last lecture. And we have seen that metals generally have ductile kind of failures, particularly metals such as aluminum and aluminum alloys. And such fracture generally occurs through three stages. Void nucleation, growth, and coalescence. Right, so this is the main mechanism of failure in ductile metals. First, as you load it, voids will nucleate and then these voids will grow, and ultimately when the voids coincide, they will coalesce into bigger voids, and that would ultimately lead to the fracture of the material. Okay. So when you have these particles dispersed in the matrix, we need to see how this nucleation and growth behavior will change. Okay. So let's talk about the first stage, that is void nucleation. So here we have particles dispersed in the matrix, and it has been shown that the voids nucleate at the particles. Although void nucleation in the matrix has been also suggested, but by in situ experiments, it has been shown that voids actually nucleate near the particles. Okay. And in particle reinforced composites, there are two modes of void nucleation. One is through particle cracking, and other is through interface decohesion. So here also you can see the interface bonding is going to play a role. In case of a weak interface, there will be a decohesion between the particles and the matrix, like how we have seen in case of fiber reinforced composite. There could be debonding at the interface because of a weak bonding. So here also, depending on the interface strength, the nucleation mode can change. Okay. So in case of a strong bonding, particle cracking is what is the mode for nucleation of the voids. And what mode will be dominant, that depends on factors such as particle size and interfacial strength. It has been shown that the mode changes from particle cracking to decohesion with increasing particle size. And the strength to fracture or ductility of such composite materials, that is, these DRMMCs, depends on the matrix parameter. And this dependence of the ductility on the matrix properties has been explained with regard to an increasing nucleation rate. Increasing void nucleation at the reinforcement phase by suppression of strain relief mechanisms at the interface. If the void nucleation rate increases, then the ductility would decrease, and this is what has been seen in composites having larger particles. So the ductility decreases with increasing particle size, and also increasing volume fraction of particles. Because when the particle size and the volume fraction increase, the nucleation rate also increases. So this explains as to why when the particle size and the volume fraction is increased, the ductility decreases. Okay, but this is not only about the void nucleation rate, which affects the fracture behavior or the strain to fracture. Other matrix processes as to how exactly the matrix behaves during the loading also have to be considered. Okay, so that aspect can be understood as to how the matrix behavior affects it when you look at the void growth and coalescence. Voids coalesce by shear failure of the matrix between the voids. And this occurs when the void height becomes equal to the inter-void spacing. Now let us look at the effect of the matrix aspects. Okay, as I was saying, the matrix properties or the matrix behavior will also affect the fracture behavior of the particle reinforced composites. So again, we can consider two cases, one with the ductile matrix and other with stronger matrix but relatively lower ductility. So in case of the ductile matrix, you would see a lot of particle cracking. And extensive void growth can be seen along the tensile direction. But hardly any lateral growth. Which indicates the constraining effect that the particles will have on the matrix deformation for well-bonded particles. And this has a huge significance in terms of the ductility. When this occurs, when the deformation of the matrix material is constrained by the presence of the particles, you can expect a higher ductility in the composite. Okay. So therefore, when the void nucleation occurs by the particle fracture mode, you can expect the hindrance to the coalescence by this constraining of the matrix flow, and this will lead to an increased elongation to failure and also higher toughness. Now, on the other hand, if you consider a stronger matrix, for example, if you consider an aluminium alloy, let's say some aluminium magnesium alloy, then the nucleation mode can change. And here you would observe lateral growth. Unlike the previous case where there was no lateral growth of the voids at all. But here in this case, a lateral growth can be observed, which indicates that the constraining effects of the particles are not there. Okay. And therefore the elongation to fractures will decrease. So here, since the matrix is stronger, voids can nucleate in the matrix. And therefore, the constraint to the plastic flow of the matrix is reduced. Which will result in a lower ductility. So as you could see here, this is not only about the void nucleation rate, but it is also about the matrix parameters or the matrix aspects as to how the matrix behaves when the composite material is loaded, right? So in the beginning, we were talking about the void nucleation rate and its correlation to the ductility. But as I mentioned, it is not only about the void nucleation which can affect the ductility, but you also need to see how the matrix will behave in the presence of the particles. Okay, so the matrix parameters will actually have a lot of bearing on the ductility of the composite material. And this difference between the nucleation mode can be also identified by looking at the fracture surface, which can be observed in a scanning electron microscope, which shows the topography, and it can show the differences that you have on a particular surface. Okay, so for the ductile matrix, if you look at the fracture surface, you will have simple features like those voids or dimples, because it has occurred through a void nucleation and growth kind of mechanism. And you can also see that the matrix necking to a knife edge before failure. Matrix necking to a knife edge between particles. And you can also observe some serpentine glide kind of features on the dimples, which is indicative of a shear coalescence mechanism that we talked about. The stronger matrix, on the other hand, will have a more complicated fracture surface. So here, as I said, there are matrix voids because the voids can also nucleate in the matrix, in this case of a stronger matrix. The presence of the matrix voids leads to a reduction in the size of the voids associated with the particles. And that would actually lead to a decrease in the macroscopic ductility of the composite. So the fracture surface talks a lot about the fracture mode or mechanism of the material, okay? And that is why whenever we try and investigate the fracture behavior of any material, including composites, we observe the fracture surface under the ACM, okay? So because you can see these kind of features on the fracture surface which will guide you to understand what would have happened during the deformation of the material. So let me show you these two different modes in a fracture surface as to how do you identify and how you can actually see what would have happened by looking at the fracture surface only. If you do a careful observation of these two fracture surfaces over here, these are two micrographs captured in a scanning electron microscope. So here you can see a particle sitting inside a void, okay? So this is indicative of a good interface bonding, first of all, and this also tells you that the void nucleation mode is through particle fracture or particle cracking, right? So even after the fracture, the particle is still bonded to the matrix, as you could see, okay? So this has broken into two halves, the particle. Here you can see one half, and the other half can be seen in the corresponding part of the fracture surface. If you identify the same area on the other part of the fracture surface, you can see the another half of this particle on that, okay, on the other part of the fracture surface. So this is indicating a ductile kind of failure where the interface bonding was good and the void nucleation mode was particle cracking, okay? But here you can see a void over here which is corresponding to the size of a particle, okay? So this tells you that there was a particle sitting over here which has actually pulled out, right? And that also indicates towards the fact that the interface is weak over here. The interface bonding is not strong, and that is why when the composite was loaded, this particle is pulled out, right? So here the void nucleation mode is the second mode that we talked about, that is through particle pull out, and this happens when the interface bonding is not that strong. You would see the same thing in a fiber reinforced composite also, depending on the nature of the interface bonding. If it is a strong interface, you would see a similar feature. Instead of a particle, you would see a broken fiber is sitting here, and the other half of that broken fiber will be found if you look at another part of the fracture surface, okay? The corresponding region, if you see, the broken half can be seen on that part, okay? And if the interface bonding is weak, you will see a hole, the size of which will be similar to the size of the fiber or the diameter of the fiber. And that would indicate that the fiber was sitting over here, but due to a weak interface bonding, it has been pulled out when the composite was loaded, okay? So this pull out fracture mode can be seen in both continuously reinforced composite as well as discontinuously reinforced composite material. But here we have seen that there is a lot of bearing on this mode on the ductility of the composite material. And with that, we come to the end of this lecture. But there is more to come on the mechanical behavior of MMCs. So don't forget to tune in. I'll see you soon. Thank you.